Across wide open fields, wind turbines are turning steadily, converting the invisible motion of air into clean electrical power. From a distance, they may look like giant fans, but each turbine is actually a standalone power plant. As the camera moves closer, we begin to see the true scale of the rotor, tower, and nacelle at the top. Three long blades rotate slowly in the wind, but every turn depends on a very precise mechanical chain. In this opening section, we move from realistic scenery into a technical model so we can see what is happening inside. A complete turbine includes blades, a hub, a nacelle, a tower, and a foundation, and every part has a purpose. The rotor is the rotating front section, made of three large blades connected to the central hub. Inside the nacelle is the machine room, where rotation from the blades is processed before becoming electricity. The tower does more than lift the turbine higher into stronger wind. It also carries cables and internal service access. Below the ground, a massive reinforced foundation keeps the whole machine stable against large wind loads. When we look at the entire system, the key question is how wind acts on the blades and creates rotation. Wind moving through the rotor does not simply push the blades, it flows around their surfaces and changes pressure. A turbine blade has an aerodynamic shape, similar to an aircraft wing that has been stretched and twisted. As air passes over the two sides of the blade, pressure difference creates lift and pulls the blade around the hub. That lift is what makes the rotor accelerate smoothly when the wind is strong enough and stable enough. Rotation at the hub creates torque, which sends mechanical power into the main shaft inside the nacelle. The energy path is clear, from wind to blades into the hub and then into the drivetrain shaft. Now we enter the nacelle, where the mechanical drivetrain is packed into a surprisingly compact space. The low-speed shaft connects directly to the rotor, turning slowly but carrying a very large amount of torque. Even though it does not spin fast, this shaft is the first point where mechanical energy enters the internal system. From the low-speed shaft, rotation enters the gearbox, the component that changes the speed of rotation. Inside the gearbox, meshing gears convert slow, powerful rotation into faster rotation for the generator. The input side turns slowly with high torque, while the output side spins faster to match the generator. The high-speed shaft receives this motion after the gearbox and transfers it directly into the generator. When we view the full drivetrain, mechanical energy moves continuously from the rotor toward the generator. The gearbox carries very large loads because it constantly transfers torque from the blades into the generator. Bearings and supports keep the shafts aligned, reduce friction, and help the drivetrain run reliably. The gearbox also needs lubrication and cooling, because friction between the gears can generate a lot of heat. Some modern turbines remove the gearbox entirely and use a direct drive design with a much larger generator. In a direct drive system, the rotor connects more directly to the generator, reducing mechanical parts but increasing generator size. In this video, we return to the geared drivetrain because it clearly shows how energy moves through the system. The high-speed shaft enters the generator, where rotational motion is about to become electrical power. Inside the generator, a rotating rotor and a stationary stator work together to create electricity. The rotor spins inside the stator, while copper windings around it experience a changing magnetic field. When the magnetic field changes through the coils, electromagnetic induction creates electric current in the wires. Electricity begins leaving the generator through cables, marking the change from mechanical energy to electrical energy. However, the electricity produced can vary with wind speed, so it is not always ready to go straight to the grid. The power converter processes the electricity, adjusting its waveform, voltage, and frequency into a more stable output. After conditioning, the electrical power is better suited to travel through the cable system inside the tower. Electricity travels downward through large cable bundles inside the tower, from the nacelle to the turbine base. Inside the tower, cables run through the hollow structure alongside maintenance access and support platforms. At the tower base, electricity enters ground-level electrical equipment before moving toward the nearby transformer. The transformer raises the voltage to a level better suited for long-distance transmission with lower losses. Many turbines in a wind farm send their electricity to a central substation before it enters the grid. After understanding the electrical path, we return to a crucial control feature, blade pitch adjustment. At the root of each blade, the pitch mechanism allows the blade to rotate around its own long axis. Changing the blade angle by only a few degrees can change how much energy the blade captures from the wind. In normal wind, the blade angle is set to create useful lift and keep the rotor turning efficiently. When wind becomes stronger, the blades rotate to reduce aerodynamic force and prevent the rotor from overspeeding. Comparing the two blade angles makes it clear. One captures energy, while the other lets more wind slip past. The pitch system is not controlled by hand. It is automatically managed using sensors and operating data. Sensors on top of the nacelle measure wind speed and wind direction, then send that data to the controller. The controller analyzes wind speed, rotor speed, generator load, and blade pitch angle before choosing the right adjustment. When conditions change, commands return to the hub, adjusting the blades to keep power output more stable. If the turbine needs to stop, the blades rotate into a feathered position to greatly reduce wind force. So pitch control helps optimize efficiency and also acts as an important protection layer for the turbine. Next is the yaw system, which turns the entire nacelle so the rotor faces the wind. Between the nacelle and the tower is a large yaw bearing that supports the nacelle and front rotor assembly. Yaw motors drive small gears against a large gear ring, slowly rotating the nacelle on top of the tower. When wind direction changes, the nacelle turns with it so the rotor can keep facing the incoming airflow. If the rotor is misaligned, some wind energy is lost and loads across the blades become less balanced. When the rotor is aligned, airflow across the rotor disc becomes more balanced and the turbine works more efficiently. The yaw system forms a control loop, sensors measure wind, the controller calculates, and motors turn the nacelle. Each yaw correction is slow and heavy because the nacelle and rotor assembly has enormous mass. When yaw and pitch work together, the turbine can maintain efficiency as wind direction and strength change. But if the wind grows too strong, the system must shift from optimization into monitoring and protection. Sensors continuously check wind speed, rotor speed, vibration, temperature, and generator load. When overload risk is detected, the controller sends commands to the pitch system and the drivetrain brake. The brake system sits in the drivetrain and helps slow the shaft when the turbine must stop or protect itself. At the same time, the blades move into a feathered position so wind passes with less turning force. As the rotor nearly stops, the turbine enters a safe state, reducing load on the gearbox, shafts, and generator. After shutdown, internal nacelle systems stabilize, but sensors and cooling systems continue to monitor conditions. Vibration is an important signal, because abnormal vibration can warn of bearing or gear problems before failure. Temperature must also be controlled, especially in the gearbox, generator, power converter, and brake system. Cooling air moves through vents and ducts inside the nacelle, helping electrical and mechanical equipment avoid overheating. When conditions become safe again, the turbine can slowly return to normal operation. The blades leave the feathered position, the rotor accelerates again, and the generator begins producing steady power. Electrical energy returns inside the generator, passes through the converter, and continues down the tower as before. Overall, a wind turbine does not just spin, it is a self-controlled machine with multiple safety layers. From the tower base, electricity passes through the transformer and cables into the wind farm electrical network. At the substation, power from many turbines is collected, controlled, and prepared for transmission. The transformer increases voltage, helping electricity travel long distances more efficiently with lower energy loss. From the substation, electricity travels through high voltage lines, leaving the wind farm and entering the transmission system. On the grid map, wind power becomes one part of a much larger energy network. Electricity is then distributed to smaller substations toward communities, factories, and other power users. One turbine produces only part of the total output, but an entire wind farm can create a much larger power flow. However, wind is not always stable. Different parts of the wind farm can receive different wind conditions. Because production changes with the wind, the grid must balance wind power with other sources and storage systems. When wind is too weak, the rotor turns very slowly or stops, because there is not enough energy to generate efficiently. When wind reaches the operating range, the rotor turns smoothly, the drivetrain works, and the generator produces power. At rated wind speed, the turbine produces high power while the control system keeps the rotor within safe limits. If the wind becomes too strong, the turbine reaches cutout speed, feathers the blades, and slows the rotor. So a wind turbine works best within a specific wind speed range, not in every possible condition. Over time, mechanical components like gears, bearings, and shafts experience wear from repeated loading. The gearbox is one of the most heavily loaded systems, so lubrication, cooling, and maintenance are extremely important. The blades also experience constant bending loads, especially near the root where forces transfer into the hub. For offshore turbines, maintenance is even harder because of distance, waves, salt water, and harsh weather conditions. The offshore foundation must keep the turbine stable against waves, currents, and constantly changing wind loads. Behind each turbine is a wake region, where airflow becomes slower and more turbulent after passing through the rotor. That is why turbines in a wind farm must be spaced carefully to reduce energy losses from wake effects. Looking back inside, we can see many systems working together: blades, shafts, gearbox, generator, electrical systems, and control. The energy path begins with wind, moves through the blades and shaft, reaches the generator, and finally enters the grid. During that journey, energy changes form, from moving air to rotating machinery to electrical current. A wind turbine is a controlled energy machine, combining aerodynamics, mechanics, electricity, and automation. Now the technical layer's close, and we return to the turbine as a real machine in the landscape. From the outside, everything looks peaceful, but inside every rotation is a complex chain of technology. Many turbines work together across a wide area, turning moving air into electricity for the power system. As the sun gets lower, the wind farm continues operating, using energy from the air that never stops moving. A single turbine is a large machine, but in a wind farm it becomes part of a much bigger energy infrastructure. Even from the outside, we can now imagine the energy path running from the blades down to the generator and grid. That is the principle of a wind turbine, using aerodynamics to create rotation, then electromechanics to create electricity. And this is how a machine that looks simple can turn wind into useful energy for people.